Optimization. We finally made it to one of our key points in the whole course on business calculus, which is how we can find optimal values in our functions of interest, such as profit, revenue, or in the case of cost, how can we minimize the average cost. I'm going to show you those examples specifically in the next video, but here we have a quick overview of how optimization takes place. Alright, so let's take the example of profit, because oftentimes the main interest will be in the optimization of the profit function. Hopefully you guys recall that profit consists of taking your total revenue and subtracting off your total cost. So your total profit function is equal to revenue minus cost. A lot of the tough part of doing optimization problems in business is going to be the formation of your revenue and cost functions with the information you've been given and the formation of your profit function after that. Okay? Let's pretend we have pictures of our revenue and our cost functions. Here's the revenue function right here, as you can see going through 0, 0. And here's our cost function right here, which usually has a y-intercept above the x-axis here. And as we talked about many times before, if we'd like to locate our relative extrema, all we need to do is take the derivative of the function of interest and set it equal to 0. Okay, so if we want to optimize profit, which is the difference between revenue and cost, we're going to set p prime equal to 0. Alright, so let's do a little calculus on that. Profit is revenue minus cost. If I want the derivative of profit, that's the derivative of revenue minus cost. Now, by the sum and difference rule of derivatives, that's equal to r prime minus c prime, and in order to locate the relative extrema, I usually end up setting that equal to 0. Sometimes it does not exist, but usually we end up setting that equal to 0. Okay, so if we have this equation right here set equal to 0, that's the same thing if we move the c prime over to the other side as saying that the r prime is equal to the c prime. And then at this point we recall that the derivative of all total functions is equal to the marginal function, the marginal quantity, and so r prime equals c prime is the same thing as saying marginal revenue equals marginal cost. That's kind of cool. So if you want to find the maximum value of your profit, if your profit is maximized at a relative extrema, then you're going to have the fact that marginal revenue is equal to marginal cost. Of course, that's assuming that your p prime is set to 0 as opposed to does not exist. If your p prime ends up does not exist, usually your equation's a little funky there, and so you'd want to take a look at your domain and figure that out. Okay, marginal revenue equals marginal cost at the location of the relative extrema in total profit. Keep in mind that relative extrema here are minimums and maximums. So when you do locate relative extrema, be sure to use the 4-step method, including the first derivative test, to classify the extrema as a relative max or a relative min. Okay, so in this sense here, let's pretend we've got this example with total revenue and total cost here. First of all, can you pick out just with your eye the location of the maximum profit? Okay, so where is the max profit? Max profit at... Can you picture the profit given a graph of revenue and cost and the fact that profit is equal to revenue minus cost? Alright, revenue minus cost, so that's the difference of two functions, right? So actually on this graph, if I want to picture my profit is going to be the distance between the two functions with revenue on top, meaning that that's a positive profit. Okay, so that is to say that if revenue is greater than cost, the profit is the distance between those two functions. Now what would happen at the intersection point? For example, R is equal to C right here. What is this? Is this a location of maximum profit, this point of intersection? No, that's not it. That means that the revenue is exactly equal to cost, and this goes back to what we were calling before a break-even point. Okay, so when those two graphs intersect, that's a break-even point. When those two graphs are as far apart as possible, with the revenue being on the top, that's where we're going to find our maximum profit. Okay, so you see how the revenue is bigger, bigger, bigger than the cost, and it looks like right about here, the distance between the two graphs is at its greatest point. Okay, you see? And so that distance represents our profit right there. And so this location right here represents a relative max in the profit function. Okay, now let's see if we can visualize what we just derived here, which is that when you set P prime equal to 0, you end up concluding that marginal revenue is equal to marginal cost. What do those marginal quantities look like on the graph? For a little bit of review, I'm bringing out my green pen, so what do you think I'm going to say about this graph? Tangent lines, that's right. We have to look at the tangent line, and the slope on the tangent line represents the marginal quantity for that total function. Okay, now this C function here looks pretty linear, so it's going to have the same tangent line each time. The slope of the tangent line will be the same exact thing each time, and so the slope of the tangent line, or the marginal cost for that linear cost function, is fixed. Alright, so then that brings us to just trying to find where is the marginal revenue, where's the slope of the tangent line on the revenue function going to be equal to the slope of the tangent line on the cost function. Okay, so let's see, this is the slope of the tangent line for the cost function. It's got a positive slope, and I'm going to picture this tangent line bringing it up to the bringing it up to the total revenue function. And you can see that exactly at this point, where my eyes kind of thought that those two functions are as far apart as possible, this is exactly the point where the slopes on the two tangent lines are exactly equal. See, this slope of this tangent line represents marginal cost. Slope of this tangent line right here represents marginal revenue. Okay, now if I try to picture what is the marginal revenue at a different point on the revenue function, looks like over here the marginal revenue is pretty high. Looks like over here the marginal revenue kind of topped off, so it's kind of low. But for this point right here, the point at which the relative max in the profit occurs, that's when the slope on the marginal revenue tangent, the slope on the revenue tangent line, which is the marginal revenue, is exactly equal to the marginal cost. Okay, so that's one way for you to look for the extrema, but keep in mind that this fact right here, which is equivalent to this fact right here, locates all the relative extrema, so you want to make sure that you use that first derivative test to confirm that you have a relative max. Sometimes you might end up with a relative min. So depending on what function you're analyzing, you might be interested in one over the other. So one more thing that I'd like to go over before we start with the concrete examples in the next videos is going to be the difference between relative and absolute extrema. So far we've only discussed relative extrema, and those extrema are subcategorized as either a maximum or a minimum. The definition of a relative max or min was the maximum or minimum value on a function compared to the surrounding nearby values. This is the key phrase right here, which defines it as a relative extrema as opposed to an absolute extrema. So let's compare that with the definition of an absolute extrema. An absolute max or min is a max or min value over the entire domain of the function. Okay, so I've got two different functions here that I've drawn, and I'm going to show us what's the relative and the absolute extremas on each one of these functions. I'll pick out the relative maximas and minimas in red, relative in red, and then absolute, I will pick those out in green so we can compare and contrast. Okay, so for the review part, like I said, we've already talked about relative extrema quite a bit, so can you locate all the relative maxes and mins on the function f of x I've shown here, and likewise on the function g of x I've shown right there. Go ahead and pause it and try to locate the relative maxes and mins. Alright, so I think that you've been doing that quite a bit, so hopefully you saw that this is a relative max, R max, right here, and then this is a relative min, R min, right there. Likewise, on the g of x function, it looks like we have a bunch of them. We're just looking for any peaks and troughs that are around, and so here I have a relative max right here, and then next to it I have a relative min. Moving over, I see I have a high peak right here, and that's a relative max. And then I've got this little trough right here for a relative min, and then I've got another relative max right there. Okay, did you guys get all those extrema? That one had quite a bit, huh? Alright, so now let's compare those with what I'm now defining as the absolute extrema, the absolute max or min, and those are going to be completely the absolute maximum and minimum of the function over a specific given domain. So in order to define an absolute max and min, we usually have to have a function over a fixed domain. So here on each one of these, I'm going to say, let's say that my domain is restricted to x inside the region from a to b, including the endpoints a and b, and likewise for g of x over there. See if you can pick out what I'm going to write down with the green pen, which is where is the absolute maximum of this function? Where does it get the completely highest y value that it'll ever get, and then the absolute min is the complete lowest value that it's going to reach. You see those there? Now I have a relative max here where my function gets pretty high up. However, as I approach b over here, you see my function gets even higher and higher. Let's see if we can pick out what's the height of f of x when we evaluate it at x equals b. It looks like it goes all the way up to here. This is f of b right here. Okay, now is f of b, is this y value higher than the y value in the relative max? Yeah, it sure is. Is it higher than every single y value that I see in the restricted domain from a and b? Yeah, I don't see any values of f that are higher than that, and that's what defines it as our absolute max. Alright, so the absolute max here is going to be f of b. For the same reason, f of a down here is going to be our absolute min. Although we have a relative min located right here, which is lower than the surrounding points, it is not lower than this point right here, and so f of a here is going to be our absolute min. The lowest value over the entire fixed domain. Alright, so let's try it again for this function over here, g of x. We're going to be looking for the absolute highest that the function ever attains, and likewise the absolute lowest that it ever falls down to. Well, we have all these little relative minimas and maximas to consider. Those might be the answer. But then again, we want to consider the heights of g of a right here, and we would probably want to consider the height of g of b right there. Actually, those might not be the answer, so I'm not going to write them in yet. Okay, so what is the absolute highest value that the function ever attains? Looks like it's right up here, right, at the relative max, and that's the lesson. A relative maximum is a candidate for an absolute maximum. The relative maximum might be the absolute maximum, but we're not sure until we compare it with the endpoints, okay? It turns out that when you find an absolute extrema, the list that you have to go down is what are the heights of all the relative extrema, and then you have to compare that with the endpoints, and then whoever is the highest and lowest value wins the award for absolute max or min. Okay, so this relative max right here, because it's the highest of all the relative maxes, and because it's higher than both g of a and g of b, that wins the award for absolute max. It's the highest value that function will ever obtain. Now let's do the same thing for relative min. You see this relative min pretty low, that relative min pretty low, but what about this value, g of a? Looks like that's even lower than either one of the relative mins. Okay, so that might be the answer. But what about this value over here, g of b? That's even lower than g of a. So it looks like this endpoint right here, g of b, because it's the lowest thing that I found all around, that's going to be the absolute min. That is the lowest value. You see it's a little bit lower than the g of a right there. The lowest or the highest thing over the entire domain. Alright, we're definitely going to try these out on a bunch of different functions which describe quantities of interest in business. But finally, I just want to show you the conclusion here when you're searching for absolute extrema. You can see from our examples, especially our example of g of x here, you can see that we really are not so much interested in all the relative extrema as we are in the single absolute max and the absolute min. right? Because maybe we're going to reach a bunch of highs and lows, but we're not going to make all those random highs and lows our conclusion. We want to know what is the very highest of the highs, what's the very lowest of the lows, and oftentimes that absolute extrema is really what we're searching for when we're trying to optimize some quantity. Okay, so when we're searching for absolute extrema, number one, we have to find all the relative extrema. And when I say find all relative extrema, that's all the stuff we learned last week where we have to or maybe the week before, we have to take the derivative, set it equal to 0, does not exist, draw the derivative sign number line, use the first derivative test to classify them, and finally conclude, here's a relative min, here's a relative max, etc. So this number one's a pretty big step, but hopefully you feel confident that you already know how to do that. Okay, step number two is going to be to find the values at each endpoint of the domain. So usually you're going to have some sort of domain that you're restricted to. As we've seen in business, oftentimes we're restricted to the fact that the x, if it's the number of items, has to be 0 or greater. And then sometimes it can't go to infinity. We have like a limited number of things, a maximum number that we could produce or sell or likewise. So those would be referred to as the endpoints of the domain. So step 2 is going to be find the values at each endpoint of the domain, and step 3 is the absolute max is the highest, the total highest out of all of number 1 and number 2, and then the absolute min is going to be the complete lowest, the lowest one down of everything that you found versus the relative extrema and the values at the endpoints. So when you're looking for an absolute extrema, all you have to do is go through all the relative extrema and then compare that with each endpoint, and then you'll locate them. Okay, so let's get started with some examples in the next upcoming videos.